Hi guys, good morning. Everybody there? Can we start?
Yes, sir.
I only very less people are there today because it's raining. Nice climate, everybody's sleeping. Hmm?
No, sir, current off.
Oh, current off. Okay. So how are you guys using this thing? You have mobile networks.
UPS, sir.
Okay. No. The thing is, Wi-Fi and all is how is it working? Like in your house?
Hotspot.
Okay. Fine. Cool. So hope you remember what we were seeing. So can someone tell me what we saw last class?
Seeing bonds, sir.
Okay, good. We started chemical bonding. Very good that you remember. Okay, so in chemical bonding, what we saw?
We are learning about ionic bonds and
Very
its
good.
properties.
Good, right? So we saw ionic bonds, how ionic bonds are getting formed, and we said that ionic bonds are very strong because they have very strong electrostatic force of attraction between the cation and the anion, right? And then, okay, before that, we saw generally how chemical bonds can be classified, isn't it? What are the types?
Primary bonds and secondary bonds.
Okay, so what is the difference between primary and secondary bonds? The clue is Dalton.
There's 100% rearrangement of electronic configuration.
Exactly, right? So there is 100% rearrangement in the electronic configuration. That means electron is completely lost or completely gained or completely shared. Eventually, that particular atom's is, I would say that particular atom's is, electronic configuration is completely changed, right? So instead of having say 7 electrons in the valence shell, after the bond would have been formed, they would have had 8 electrons in the valence shell, right? Okay, so then we went on to secondary. So say secondary, obviously it is not going to have 100% rearrangement. I'm going to have only partial rearrangement happening, right? So then we went on to see, okay, then we saw what are the types of primary bonds, what can be secondary bonds. I gave you some examples, right? And then we went on to see ionic bonds, right? In the ionic bonds, as you said, we saw about how ionic bonds are formed, what are the properties of ionic bonds. So yes, can you come up with the properties? What are all the properties of ionic bonds we saw?
Mostly they are solid.
Okay, yes, they're mostly, okay, correct.
Solid
Then
in water.
they're highly soluble in water. What was the quote I asked you to remember for
Like
solubility?
dissolves,
Very good. Like dissolves like.
and they
So
have
that means
Highly polar. They have a lot high melting point and boiling.
they have high melting points, boiling points, right?
Highly
So,
polar.
yes, obviously that's what I was about to tell, right? So when I say like dissolves like, polar solutes will dissolve only in polar solvents. Non-polar solutes will dissolve only in non-polar solvents. Okay. So now how do you decide whether the compound is polar or not? Or the bond is polar or not?
Based on electronegativity.
If it is H and H means it is non-polar, sir. If it is H and Cl means it is polar.
Okay, everything is correct. You said it's based on electronegativities. It is just electronegativity
Electron density, sir.
No. Like electron density is everything. You're telling like there and there, all those points are there. Just connect it. So is it just the electronegativity or is it something else? Like is it, when I look at the bonding atoms, so I should have dash in electronegativity. What should I have?
High difference in electronegativity.
Exactly. That's what you need to tell. There should be difference in electronegativity. If there is no difference in electronegativity between the bonding atoms, then it is not going to be called as polar, right? So because of the polarity, because of the difference in electronegativity, the electron pair, that is the bond pair which is there, the electrons are shared, is not going to be at the center. It is going to be more and more towards the more electronegative atom, thereby inducing a partial negative and partial positive charge on the atoms. And these are what are called as polar, right? And then we saw one more thing. Okay, what are other properties?
Lattice energy.
That's what I was expecting. Yes, what do you mean by lattice energy, people?
The crystal structure of the ionic compound.
Lattice means crystal structure. Yes,
I
lattice
need to
talks about
break the lattice structure.
correct. So basically, lattice means it talks about the crystal structure of the particular compound, right? So lattice energy means the energy required to break the lattice, right? Energy required to break the lattice. So we'll see more about this lattice energy when I go for thermodynamics, right? That will be say 2-3 chapters away, right? So when I go for thermodynamics at that time we'll see it, right? So yeah, these are all the things we saw last class, right? So that's it about ionic bonds, okay? So now we'll go to covalent bonds, right? So we first see how is it formed and various theories proposed for shape of the molecule, structure of the molecule, the bond lengths, all these things. We'll look into it. Okay, fine. So we'll move on to covalent bonds. Again, this comes under primary types of bonds only, isn't it? Because there is complete rearrangement of electronic configuration. Cool. Right. So we know how covalent bonds are getting formed. We say that it is going to have mutual sharing of electrons. By that, a chemical bond is getting formed. Okay. Right. So before we move on to see, in simple words, in a layman language, right? What do you mean by a bond? In simple words, how will you tell it?
Force of
Force of
attraction.
attraction.
That's it. Very simple, right? It's going to be about the force of attraction. In case of ionic compounds, the force of attraction was between the cation and the anion, the positive charge and the negative charge, right? So here there are no charges, isn't it? Right? Here there are no charges, there is no cation, there is no anion, right? But somehow we have to account for this force of attraction. How these covalent compounds are able to stay together in a bond, or how they have the force of attraction, we have to see, right? Okay. So now what we are going to do is, say I am going to take two atoms. Let me take two hydrogen atoms, and two hydrogen atoms are going to come together to form a HH bond. So basically, this bond I'm going to talk about, this H2 HH bond. Okay. So now we'll assume a case like this, right? We are going to take the hydrogen atoms which are very, very, very far away from each other, or in a proper term, if I have to put it, I will tell that I'm going to start the case where I have the two hydrogen atoms are isolated. Isolated means, what do you mean by isolated atom?
Free reactions.
Sorry?
Which are free of
Atoms.
reactions.
Free of reactions? No.
Interaction.
Free of interaction. Okay, correct. So basically, there should not be any force of attraction or force of repulsion acting on that particular atom. So that particular atom is what is called as isolated atom. Cool. Right. So I am going to take the two hydrogen atoms to be very, very, very far away from each other. Right. That means they are, say, I call it as HA and HB. These two hydrogen atoms only, just for making a difference. I'm just writing it like this. I have, so basically, they are very far away from each other, they are isolated. Okay. So now what I'm going to do is that I am going to bring them closer. Right? I am going to push these two hydrogen atoms to little closer, to a point where the attractive force starts. Right? To a point where attractive force starts. Now the question is, sir, where is the attractive force coming from? Just if I keep them in some distance, right? There is going to be some kind of attractive force coming into the picture. Now the question is, where is the attractive force? Where, like, between what and what I have the attractive force? Do you have any clue, guys? The attractive force is going to be between what
Nucleus
and
of one with the valence electron on the other atom.
Very good, very good. So obviously you can understand that these two hydrogen. Okay. So I know these two hydrogen atoms, both of them will have a nucleus, right? And I know in each of these valence shell I have one electron. Correct. Okay. So now what is going to happen is when they're very far away from each other, when they are isolated, there is no interaction, right? So now when I'm trying to little closer, I bring them. Right? What is going to happen is the nucleus of this and the electron of this are going to have some attractive force, because nucleus is positively charged, electron is negatively charged. Same goes with the other atom also. The nucleus of this atom and the electron of this atom are going to have some attractive force, right? So if I just try to bring them little closer, I don't have to do anything. They will eventually become more and more and more closer because of the attractive force. Isn't it? They'll become more and more closer because of the attractive force, right? Now, If they're very far away from each other, no force. If they're little closer, the attractive force starts and the atoms moving closer and closer and closer. Now what is going to happen? Now when the atoms keeps on coming closer, right? When the atoms keeps on coming closer, obviously one more force which is going to come into the picture, and obviously that is going to be my repulsive force, isn't it? That is going to be my repulsive force. Repulsion between what? When they're very, very close to each other now, right? When the attractive forces started, they came closer, 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 closer. Now they are very close to each other, right? Now what is going to dominate? Now the repulsive forces are going to come into the picture, right? Repulsion between what? Nucleus of this and nucleus of this, electrons of this and electrons of this are going to have repulsive forces coming into the picture, right? So I'm going to choose a point, right? I'm going to choose a point between these two extremes. That means when the attractive forces are there, right, that particular thing I'm going to take. If they're going to bring little closer, more closer, the repulsive forces are going to dominate, right? So now please understand, bonds are formed in chemistry because the atoms can attain stability. That's the point, isn't it? Right? The chemical bonds are formed between two atoms, so that particular atoms involved in the chemical bond are going to attain stability, right? So we have to speak in terms of energy here, right? We have to speak in terms of energy here, and please understand, energy, I don't know whether you know this, energy is equal to F dot ds, basically force into displacement, right? So here I have two kinds of forces existing. One is the attractive force, another one is the repulsive force. Okay, so I have to choose a point, right? I have to choose the distance between the hydrogen atoms such that neither attractive force nor repulsive force are going to exist in the picture, right? So when they are little far away from each other, attractive force dominates. When they are very, very close to each other, repulsive forces dominate. So in between these two positions, I have to choose the position of, you have to choose the distance of the hydrogen atom such that this force will become zero. That means the attractive forces are going to cancel out the repulsive forces. That means the net force acting on that particular system is zero. The net force acting on that particular system is zero, right? So now if you have some idea now, right? So if I put this in the form of a graph, right? If I put this in the form of a graph, I think you'll be able to get the point what I'm saying, right? So end us till now, guys. Anyways, don't worry. Even if you don't understand, you will understand it now. Okay. Right. So let me draw a graph. Now the graph is in the x-axis. It is actually going to be the internuclear distance. Basically, what is internuclear distance? The distance between the two nuclei, distance between the two hydrogen atoms, right? And this I call it as R naught, some variable. Okay. And in the y-axis, I'm going to have potential energy. In the y-axis, I'm going to have potential energy, right? So now when the internuclear distance is very, very high, when the internuclear distance is very, very high, I'm going to call the hydrogen atoms as isolated atoms, isn't it? Say now at this point, say at some point when the internuclear distance is very, very large, right? Say the hydrogen atoms are isolated, right? The hydrogen atoms are very far away from each other, right? Now what I'm going to do, I'm going to bring them little closer. I'm going to bring them little closer so that the attractive force kickstarts. Now what is going to happen? Since the attractive forces is keeping on increasing, then so they become more and more closer, the energy is going to decrease, right? The energy value, I would say, you can see that this is negative value. You can see that this potential energy I'm putting into the negative y-axis, right? So I would say the atoms are going to become little more and more and more stable. That's what I'm trying to say, right? Now, like, how do we get this? Now, when the atoms are isolated, they have very high energy, right? Because they're unstable, right? So the very reason why they are coming together to form a chemical bond is because these two hydrogen atoms wants to get stable, isn't it? So obviously, when the atoms are very far away from each other, right? When the atoms are very far away from each other, that means they have very high energy. They are not stable, right? So definitely they will have some very high value of energy here. They will have very high value of energy. Like, okay, right? So now, when these atoms comes closer, they are going to start attaining stability. They are going to start attaining stability, and they will start attaining stability by losing energy. They will start attaining stability by losing energy. Is it not? Because energy and stability are inverse related. We already saw about that, isn't it? So when the atoms comes closer, they're going to lose energy. They're going to keep on losing energy till a point. Till a point. And after that, the repulsive forces are going to start. Again, the energy value is going to get absorbed.
Sir,
Okay, we'll try to see. Yeah.
Sir, the energy loss will be equal or not, sir? Like on
Energy loss will be equal to what?
The energy loss will be equal or not, sir? Like in both hydrogen atoms, if they are trying to.
Oh no. We are not speaking about individual hydrogen atoms here, Kanna. We are going to see this as a system. Together, the energy is what is happening.
Sir, both the hydrogen atoms will lose, no, sir. Both.
Exactly, both the hydrogen atoms will lose energy. Correct.
Okay, sir.
Understood?
Not only
Right?
one will
So,
come.
no. Both as a system. Yes, Kanna.
Here we plotted potential energy in negative y-axis, no, sir?
Exactly.
Why, sir?
Yes. That's what I'm telling. It's because in chemistry I have a sign convention. Hope you remember, right? Whenever energy is absorbed, right, I say that it is positive, and whenever energy is released, I say energy is negative, isn't it? So
Yes,
now
sir.
what you're seeing here is that when the atoms are very far away from each other, they have high energy and less stability, right? So when the bond formation is going to start, energy is going to get decreased. Is it not? That means what? Energy is going to get released. So that's why I have a negative axis here.
Okay, sir. Understood, sir.
Understood? Right? You can even have it in the positive axis. It's all about you. But I'm just going by sign conventions, nothing else.
Okay, sir.
Okay, cool. So they have very high energy. Now the attractive force starts. Now the energy is going to keeping on get released. See, this particular curve tells me that the energy is keeping on releasing from the system. It goes out, right? And it's going to become more and more and more stable, right? Now there is going to be a point, say at this point, when they are very, very close to each other, right? Now the repulsive forces starts. I would say the repulsive forces dominates. Right? So at this point, if you try to bring them little more closer, the repulsive forces will try to dominate. So thereby, again, they will destabilize the atoms. Okay. So now what is going to happen? Now I'm going to see that the energy value is keeping on increasing, and it might even go above the positive axis, above the origin. Okay. Now what do you see from this? Now at this point, I would say this particular point is the point of interest for me now. Right? This particular point is the point of interest for me now. At this point, the attractive force will be equal to the repulsive force. Right? At this point, the attractive force will be equal to the repulsive force. And obviously, and this is where I have the minimum energy. You can see that this is where I have the minimum energy. Right? And this is where I tell that a bond is formed. Right? This is where I tell that the bond is formed. Right? So obviously after that the repulsive forces are going to start. So you see that the energy is getting actually absorbed. So you can see that the energy is actually becoming more and more and more positive. Right? Energy is going to become more and more and more positive, indicating that they are going to become more and more unstable. So that won't happen actually.
So
Right?
what is
So
FE and FR, sir?
Sorry?
What is FE and FR, sir?
FA is the attractive force, FR is the repulsive force.
Okay, sir.
Right? So those two at this point will become equal, right? So obviously this is the point where I have minimum energy, maximum stability, right? This is the point where I have minimum energy and maximum stability. Okay,
Sir, then,
so this is the yeah.
Sir, then where will the electrons join, sir? Like where will the atoms join, sir?
So I'll be able, that's what, like you would have seen, okay, I'll be able to represent it like this. So, okay, now the atoms are isolated. So at this point, how will I represent? I can represent it like this. Say now I have two hydrogen atoms and these two electrons are shared, HA, HB. Now you can see that they are little very close to each other and the electron pairs are shared in between them. Right? So this is how I represent.
Sir, so the arrow marks are the energy.
Arrow marks are the?
Energy.
Which arrow marks?
So this one, like, so this one, sir, which is going towards the positive x-axis.
Yeah. This basically is the curve. This basically is the curve between R naught and the pedal energy. So after this point, this is the ideal position.
No, sir,
If I try,
what that indicates, sir? What that curve indicates, sir?
okay, so this curve indicates where I'm going to have minimum potential energy, right? Wherever I have minimum energy, that is where I have maximum stability, and that point I'm going to call that as bond formation is getting formed. Bond formation starts. That's it. Bond formation is there. So this is the point. This is the point where I have minimum energy. So guys, like only thing you have to remember is energy and stability are inversely related. That's what you need to understand. So this is the point where I have minimum energy, right? So in all of these curves, this is the point where I have minimum energy. So this is the point where I say bond formation is there, right? So this is the point where I have this kind of structure coming into the picture, right? So after this, if you try to bring them any more closer, it is going to become unstable because the repulsive forces will gonna start. Or I can even say, if I draw a line here in this area, that is before this area which I'm talking about, in this area FA dominates, that is attractive forces dominates. That's why they're able to come closer and closer and closer, right? At this point, what is going to happen? At this point, the attractive forces are equal to the repulsive forces, right? Now at this region, what is going to happen? The repulsive forces will be greater than the attractive forces. That's what it is.
So the electrons will split.
Electrons?
Will split.
Electrons will not split. Basically, if you what you have to understand is, say now, if I go to this point, right? If I go to this point, after this point, what I'm seeing is that the energy value is becoming positive. What does it indicate? Whenever energy value is positive means I have to supply energy, isn't it? Whenever energy value means the energy is getting absorbed. So when they're very close, that the repulsive forces are going to dominate, you have to supply energy to bring them any more closer. It's like I have a north pole of the magnet, I have a north pole of another magnet. So will you not give your force to bring them closer because they will be repelling each other? The same analogy can go here also. Are you able to understand?
Yes, sir.
So what I'm trying to tell you is, say I have a north pole of the magnet, north pole of another magnet. They will repel, isn't it? But still, I don't know whether you have tried. I have tried this. I have tried to bring them closer, even though they will repel. So what you are doing there, basically, you are supplying energy. You are putting in your efforts to bring them any more closer. The same thing can be told. This is the point. After this point, if at all you want to make them any more closer, you actually have to supply energy. Right? That is actually unstable because you are supplying energy, the energy of the system will increase, thereby it becomes unstable. Okay? So now, okay, so at this point, the attractive forces dominates, at this point, the repulsive forces dominate, at this point, both the attractive force and repulsive forces are equal, the net force of attraction is 0, and say the bond formation starts, and the bond formation is there at that point. So this is how a covalent bond is getting formed. Right? Because of the attraction between the nucleus of one element, atom, and the electrons of the other atom, and vice versa. The nucleus of this and the electrons of that. Okay, so hope you got this clear. What is happening? Cool. Now we'll try to see what can be the structures, how are we going to draw the bonds, and all that. Right? So hope you everybody got the picture clear. What is happening? Please give me a yes, guys.
Yes, sir.
Yes, sir.
Okay, fine, cool. So this graph is little important, right? Okay, now we understood how a covalent bond is getting formed. Right. Okay. So now what we'll do is this covalent bond was explained by different scientists. Right. This covalent bond was discovered by I would say not discovered. Was being studied by different scientists, and we'll see what they said, right? So first one we already know, that is my Lewis theory, right? Lewis dot structures. You would have studied the dot structures which you write, right? So Lewis theory. Okay, fine. So we see that the atoms are going to become stable by losing energy, right? Now we have to actually understand why is there a change in electronic configuration, right? Obviously, I know that there will be change in the electronic configuration. Why is there a change in the electronic configuration? We already know the answer because Lewis said that, and we didn't even know that it was Lewis theory. We studied it. It's basically going to be based on octet or duplet rule. Right? It is going to be based on octet or duplet rules. So we already know what is octet or duplet. Octet rule says that for the atom to become stable, I need to have 8 electrons in the valence shell. And duplet says that if at all octet is not possible, I would say duplet will work only for 2 elements, or I would say 3 or 4 elements. They say that if I have 2 electrons in the valence shell, again, that is going to become stable. Okay, fine.
So that's duplet is for helium, beryllium.
Yeah, correct. Only for the first shell.
Okay.
Because in the shell, in the first shell maximum itself, I can have only 2 electrons, right? So obviously, duplet rule is only for first shell. Basically, 1 electron is lost. For example, in the case of lithium, 3 electrons are there. 1 electron is lost. In the valence shell, I'll have 2 electrons, like that.
Understood, sir.
Right? Cool. So it is purely based on octet or duplet rules. Okay, so that means I need to have 8 electrons in the valence shell or 2 electrons in the valence shell. So let me draw the structures. Like you see, guys, you have to practice a lot. The Lewis dot structures are going to be actually very important. You'll be using this throughout your chemistry, 11th and 12th chemistry. Okay, fine. So let me start with something very simple. Like you already know this, right? But still, I'm just giving you a recap, and then we'll go for some complex molecules. Okay, fine. So let me start with, say, what do you want? You want O2? Right? I'm going to do it for oxygen molecule, right? So now please understand, I'm going to draw something called as Lewis dot structures. These dots which I'm going to write are going to indicate the valence electrons only. You have to use only valence electrons. Yes, Kanna? Yeah.
There is theory is like, is it inspired from octet or duplet rule, or it is what, sir?
No, Lewis was the one who told octet or duplet. That's how it is.
Oh, okay, sir.
Yeah, right. So he was the one who told that 8 electrons, if it is there, it is stable. Okay, fine. So we have to use only valence electrons in the picture, not the inner electrons. Please be very careful, right? So if I take the 2 oxygen atoms, if I take the 2 oxygen atoms, right? So I know oxygen atom is having 2,6 as the configuration, right? 2,6 as the configuration. That means each of these oxygen atoms will have 6 valence electrons, isn't it? Right? So let me put it here: 1, 2, 3, 4, 5, 6. Done. So again, you saw there are 2, 6, right?
286.
286 is for sulfur.
Okay.
Right? Okay. So done. So these two, this is done. So now say for this oxygen atom, say I'll use different representation: 1, 2, 3, 4, 5, 6. Okay, fine. So now here you see that this oxygen atom requires 2 more electrons to satisfy its octet. Again, this oxygen atom requires 2 more electrons to satisfy its octet. So what is going to happen? They're going to come closer and closer and closer, and these 2 electrons and these 2 electrons are going to get shared between these 2 oxygen atoms, so that both these oxygen atoms are going to satisfy their octet, and so it is going to become stable. Okay, so now very simple. This oxygen atom will take these 2 electrons, this oxygen atom will take these 2 electrons. So you'll see that both of them got stable, right? And please understand, guys, whenever 1 electron pair is shared, 1 covalent bond, right? So 1 electron pair is equivalent to 1 bond. Right? Now, how many electron pairs are getting shared here? 2 electron pairs are getting shared here. That is 1 electron pair. I would say this is 1 pair. Right? And there is another pair of electron getting shared. So you will see that 2 bonds will be getting formed. So O double bond O is how I'll write it. Right? And you have to represent the other electrons also. Okay. Now, right. In the valence shell, right? In the valence shell, if I'm going to make all these bonds, there are going to be 2 types of electrons. One are what are called as bonding electrons, right? One are what are called as bonding electrons. The other one are what are called as lone pairs of electrons, right? The other one are what are called as lone pair of electrons. Okay, so what is the difference between these two? Bonding electrons are the one which involves in bonding, or I would say bonding electrons are the valence electrons which actually involve in the bond formation. Okay, and say lone pair of electrons are the one which are there in the valence shell but not involving in bonding, So if I look at this picture here, right, so you see that these two electrons and these two electrons are actually involving in bonding. So this electrons, I'm going to call it as bonding electrons, right? But if you look at these two oxygen atoms, therefore say for this oxygen atom there are 4 more electrons which are not involving in bonding. 1, 2, 3, 4, right? There are 4 electrons in this oxygen atom and 4 electrons in this oxygen atom which are not involving in the bonding, right? So these are what are called as lone pair of electrons. These are what are called as lone pair of electrons. So you have to know this, right? What are bonding electrons? What are lone pairs of electrons is very, very important. At least not now, but when I go for the next series, right, it's actually very, very important. Okay, so done. So this is about oxygen molecule. Oh, okay, I have to represent it like this also. See, the bonding is done. This is the bond structure. This is the Lewis dot structure. This is the bond structure, right? And each oxygen atom has 2 lone pairs. Or, 2 lone pairs. So this is how I represent oxygen molecule. Okay, like this. Cool, right? Okay, fine. We'll do something complex. Okay. Guys, can we do ammonia molecule? Okay, can we do ammonia molecule? See, why am I not concentrating much? I can start with hydrogen, nitrogen, and all these simple things I can do. But you already know this. You already studied this. That's why I'm not going much into it, right? Say, let me do it for ammonia molecule. Okay. Fine.
Sir, can I do for aluminum, sir?
Aluminium. Aluminium will generally form ionic compound. It will not form covalent compound, right? Yeah, it is not like it is never going to form covalent compound, but if it forms, it is little complex. We'll see that. Wait for it, right? We'll do for, so if you have any other simple molecules, we'll do. Aluminium is not the case. You want to do for something else other than ammonia? Okay, fine, cool. So nitrogen and ammonia I'm going to take, right? So there are 2 elements here, right? And obviously for hydrogen, duplet only can be satisfied because it has only 2 shells, right? It has only 1 shell, obviously, right? And nitrogen, for nitrogen, I have to satisfy octet, right? Okay. So let me put it like this. Now nitrogen is having 5 valence electrons. So nitrogen will have 2, 5 as the configuration. So you see that there are 5 valence electrons. Okay. So let me put it like this. 1, 2, 3, 4, 5, right? And each hydrogen atom is having only 1 electron, right? Say hydrogen atom 1 electron, hydrogen atom 1 electron, hydrogen atom 1 electron. Okay, right? Now let me do it for hydrogen first, right? Now each of the hydrogen atom requires 1 more electron to satisfy its octet, isn't it? Because there are already 1 electron. So each of these hydrogen atoms require 1 more electron to satisfy its octet. So you'll see that this hydrogen atom will take up this electron. Done. This hydrogen atom will take up this electron. This hydrogen atom will take up this electron. Done. Okay. Now I have to satisfy for octet of nitrogen. Right. Now nitrogen already had 5 valence electrons. Nitrogen already had 5 valence electrons. So obviously it requires 3 more electrons. So all the 3 electrons from each of the hydrogen atoms is taken. So this is how. So now I told you 1 pair of electrons shared 1 covalent bond. So you see that there is 1 pair of electrons shared here, 1 pair of electrons shared here, and another pair of electrons shared here.
So which is the lone pair of electrons, sir?
Coming. You tell me which is the lone pair of electron. This is the lone pair of electron, right? Is it not? So this is the valence. Okay, wait. So now the thing is, I have 3 bonds done, right? 3 bonds done, right? Okay, there are 5 valence electrons. Out of that, 3 are involving in bonding for nitrogen. 1, 2, 3. 3 are involving in bonding for nitrogen. So obviously there should be 2 more electrons which are there in the valence shell, which are not involving in bonding, and that is what is my lone pair. So you can see these two electrons are actually not involving in bonding, so I represent it like this. Understood? Right? Okay, so that's about ammonia molecule, right? So like this, you will be able to draw the structures, draw the covalent bonds for any of the molecule, right? See, the thing is, there are going to be certain cases. There's going to be a good number of cases where octet or duplet is not the criteria, right? The octet or duplet is not the criteria. So sometimes what happens is I can have more than 8 electrons in the valence shell, right? Or sometimes I can even have less than 8 electrons in the valence shell. All these things are possible, right? So that is the main drawback of Lewis theory, right? The main drawback of Lewis theory is that there are species which have more than 8 electrons in the valence shell, or say they have even less than 8 electrons in the valence shell. That is one of the problems. So basically, more than 8 electrons or even lesser is possible, but that is not explained by Lewis, right? And a second point is that yes, it speaks about how the covalent bond is getting formed and all that, but it does not talk about the shape or say the strength of the bond. All these things are actually not spoken about, isn't it? The shape of that, there is nothing indication about the shape of the molecule or say how strong the bond is. Nothing is told about that, right? So these are the main drawbacks of Lewis theory, right? These are the main.
Point, sir.
I'll tell you. I'm going to give you examples. So now, till now, what you understand is nitrogen atom is having 8 electrons in the valence shell. Last case we saw that oxygen atom is having 8 electrons in the valence shell, right? But there will be certain compounds in which the element can have more than 8 electrons in the valence shell, or say in sometimes I can even have less than 8 electrons in the valence shell. All these things are possible. I'll give you examples, right? So second point talks about the shape and strength, or say all the other bond parameters are actually not explained, right? Okay, so we'll see what are these examples. How can I have more than 8 electrons, or say how can I have less than 8 electrons? We'll
So if you have lesser amount of electrons than 8, then you can apply octet or duplet, no, sir?
Correct. So duplet is only for hydrogen. I would say only for few elements: hydrogen, helium, lithium, and that's it. Only for these three elements it will work. For all the other elements,
you can apply octet, no, sir, for the lesser.
Let's see. See, when I give you the example, you'll try to understand. Wait for it. Okay. See here. Okay. Hope you have no doubts here. Say I have DF3, right? Boron trifluoride is the compound. Okay. Now, if I look at this compound, boron is having atomic number of 5, right? So it will have 2, 3 as the configuration, right? 2, 3 as the configuration, right? Now, fluorine atom has 7 valence electrons, so it requires. So if I try to draw the Lewis dot structure, so even though this, fine, okay, we'll do this. So I have 3 valence electrons for boron, 1, 2, 3 valence electrons for boron, right? And each of the fluorine atom is going to have 7 valence electrons, isn't it? Each of the fluorine atom is going to have 7 valence electrons. Say 1, 2, 3, 4, 5, 6, 7. Again, 1, 2, 3, 4, 5, 6, 7. Again, one more. 1, 2, 3, 4, 5, 6, 7. Done. 3 fluorine atoms. I'll drop this 2, 3 so that it becomes clear. Okay. So I have 3 fluorine atoms and 1 boron atom in the picture. Okay. Fine. Now fluorine atom requires it requires 1 more electron to satisfy its octet. It already has 7 electrons, so it requires 1 more electron to satisfy its octet. So obviously each of these 3 fluorine atoms will take 1 electron from boron to form octet. That fluorine atoms, no problem. Okay. Now look at this. Now boron has 3 valence electrons, right? So now it is giving only 1 electron to each of the fluorine atom. right? It is giving one electron to each of the fluorine atoms. See, remember, it is mutual sharing. If you give, you take. If you don't give, you don't take. It's like that, right? If at all I give 1 electron, I can take only 1 electron. If I give 2 electrons, I can take only 2 electrons. It's not like one thing gives electron and the other one doesn't give. It's not an ionic bond. So here it is democracy. Right? That means if you give, you give. I mean, I will give. If you don't give, I will not give. It's like that. So you see that this boron atom is giving 1 electron to fluorine. So it can take up only 1 electron, right, from fluorine. So obviously, this electron will be taken, this electron will be taken, and this electron will be taken. Yes. So this will be the number of electrons in boron. So you see, already 3 electrons are there, right? And you can see that each of the fluorine atom is giving 1 electron to fluorine. So what will happen to boron's configuration now? It will become 2, 6. It is not 8 electrons. Are you able to understand now? I think it was who asked that doubt? How 8 electrons? Mithun Krishna. Okay. Mithun Krishna understood. How is it like this?
Sir, but then this compound will not stable, no, sir?
Yeah, it looks like that. It's because you know only Lewis theory till now, right? So the thing is, octet or duplet is not the only criteria for stability. Okay, you will see that when I go for more and more theories, you will see how and all I can bring in stability.
Okay, sir.
Okay, so till now, please understand that octet or duplet is actually a very common criteria people take, right? But that is not the only criteria. Okay, fine. So this is the case for BF3. So in this case, you saw that I have this
lone pair of electrons, sir.
Yeah, this now. Okay, you tell me. Boron has any lone pair of electron in this case?
No, sir.
Cool. Fluorine has any lone pair of electron?
Yes, sir.
Yes. So now if I try to draw the structure properly, say fluorine, 1F, second F, and third F. Boron doesn't have any lone pair, but fluorine atom has. How many lone pairs each fluorine atom has?
7.
6.
6 electrons which are not paired. How many electron pairs are there? How many lone pairs of electrons?
3 lone pairs.
Exactly, right? So 1, 2, 3. Totally 6 electrons. So you can see that out of the 7 electrons in fluorine in the valence shell, 1 of them is only involving in bonding. Only 1 of them is involving in bonding. Correct? So obviously the other 6 electrons are not involving in bonding. So 6 electrons means 3 electron pairs, right? So I have 3 lone pairs on each of the fluorine atom. This is how you represent it. Okay, right? So now you saw that I can have even less than 8 electrons in the valence shell. Let me take a case where I have more than 8 electrons in the valence shell. Okay, right? So please take down the structure. Please don't look at the board and just listen. Right, we'll move on. Okay, fine. We will take some molecule which you are familiar with. I'm going to take sulfuric acid. Okay, I'm going to take sulfuric acid, right? H2SO4. Okay, fine. Now, so here the central element will be sulfur. Okay, now sulfur, you can see that it is going to have 2, 8, 6 as the configuration, right? So let me put it 1, 2, 3, 4. 1 second. Okay, so 1, 2, 3, 4, 5, 6. No problem. Okay, I'm going to have oxygen atoms also. There are 4 oxygen atoms. Okay, say 1 oxygen atom. Or, so for making it simpler, what I do is I go for SO4 2 minus. So I just remove the H plus. The same thing is going to come. I'll tell you where the H will come. Don't worry. Right? So instead of H2SO4, we'll do it for SO4 2 minus. 2 H plus are removed. Okay. So let me see how are you going to draw the structure. Okay. Now, what you can understand here is I have SO4 2 minus. Okay. Now, the question is, which is going to have the negative charge? Is it going to be the sulfur atom or is it going to be the oxygen atom? You tell me.
Yes, sir.
Sulfur.
Sir.
Okay. Any reason why are you telling this?
Sir, because it needs 2 electron to fill its valence cell, because it has. It needs
No,
two
no, no, no,
electrons.
no, 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 no. That is not the way you see it. So basically, SO4 2 minus everything already everything after a duplet whatever is satisfied. That's what you need to know, right? So whenever this kind of case comes, whenever you have a polyatomic ion, what do you mean by polyatomic ion? There are two types, more than one type of atom present, and that's an ion like this. Say sulfate, sulfite, ammonium ion. So many things are there. Or like answer this question now. I have OH minus. The negative charge goes to which element? Did you understand the question? I have OH minus hydroxide ion. The negative charge goes to which element? Hydrogen or oxygen?
Oxygen.
Why? So that you can understand. So duplet octet is not for this. So the thing is, whenever you have a polyatomic ion, you have to make sure, if at all I have a negative charge goes to the more electronegative element. That's it, right? The negative charge goes to more electronegative element. Positive charge goes to less electronegative element. So please understand this. Whenever you have a negative charge, it goes to more electronegative element. And obviously, when I have a positive charge, I would say less electronegative element will take up the positive charge. I say more electropositive element will take up the positive charge. Now tell me, so now you understood why oxygen is having the negative charge, because oxygen is obviously more electronegative than hydrogen, right? That it only will keep the negative charge, right? Same way in this case, you tell me now, which will have negative charge? SO4 2 minus.
Yes.
Which is more electronegative, sulfur or oxygen?
Sulfur.
Oxygen, sir.
Okay, so it is actually oxygen atom which is more electronegative. So please understand what we saw in periodic table. Oxygen and sulfur belong to the same group, right? Down the group, what happens to electronegativity?
It decreases.
Sir, oxygen is 16,
correct.
no, sir.
Oxygen is
16, no, sir. Electron
16.
configuration.
2,6 is the configuration. 8 is the atomic number. 2,6 is the configuration.
I took atomic mass, sir, to.
Atomic mass is 16. Okay.
I took that one to compare, sir. Sorry, sir.
Okay. Anyways, so the thing is, down the group I do electronegativity decreases. So obviously oxygen is more electronegative than sulfur. Okay. So if I keep in the mind, so you can understand that I have 4 oxygen atoms, right? And 2 of them are going to have -1 charge. 2 of them is going to have -1 charge. Sir, you can ask me, sir, why didn't you take one of the oxygen atom to have -2? That's a nice question, right? So I'm telling there are 2 minus charge, 2 minus is there. I'm telling out of the 4 oxygen atoms, 2 of them are going to have -1 and -1. Why didn't I take the 2? One of the oxygen atom is going to have -2. Can you come up with an answer for this? Do you understand my question, what I'm asking?
Sir, could you repeat the question?
So what I'm telling is, you will see, say these 2 oxygen atoms, say there are 2 oxygen atoms that are having minus and minus. Okay, why didn't I take like this 2 minus?
Because that
Now you
it
understood?
itself would be a covalent bond.
Itself would be a covalent bond. Itself would be a stable. It's already stable, right? If I have O2 minus,
And stable already.
it's already stable, right? Oxygen has 2,6 configuration. If I had 2 more electrons to it, it is already stable. Then what is the point of this coming into the bond formation? Are you able to understand? right?
Yes, sir.
So oxygen is already having 2,6 configuration. It requires 2 more electrons to satisfy its octet, right? So that is why I don't take 2 minus. 2 minus, if I put already it has 8 electrons, then how will it form bonds here? Understood. So instead of taking one oxygen atom to have 2 minus, it's basically 2 of the oxygen atoms are going to have 1 minus and 1 minus. Another 2 oxygen atoms are neutral. There are 4 oxygen atoms, right? So 2 of the oxygen atom are going to have -1, -1. The other 2 oxygen atoms are neutral. Just give me a second, guys. 1 second. May sound கேக்குதுங்க. So cool. So what I was telling, yeah. So 2 of the oxygen atoms are having -1, -1. Other 2 oxygen atoms are neutral. There is no charge in that. Okay. So now we already know oxygen atoms are having 2,6 as the configuration, right? So if I say O minus, can I say they will have 2,7 as the configuration? 1 more electron is added, correct? So for these 2 oxygen atoms, I'm going to have 7 electrons in the valence shell, and for the other 2 oxygen atoms, I'm going to have 6 electrons in the valence shell. Okay, fine. So let me fill this up. So I have 1, 2, 3, 4, 5, 6, 7. Because it's a negative charge, I have a negative charge here, right? And for this also 1, 2, 3, 4, 5, 6, 7. Yeah, again I have a negative charge here. And these 2 oxygen atoms are neutral, so I'm going to have 6 electrons in the valence shell. No problem. So 1, 2, 3, 4, 5, 6. Done. Same way 1, 2, 3, 4, 5, 6. Done. Right. Let me do it for the oxygen atoms first. Okay. Always it's better to do for the side atoms rather than for the central atom. Central atom you always do at the last. Okay. Fine. So oxygen atoms are here, right? So this oxygen atom is O minus. It is already having 7 electrons in the valence shell. So can I say it requires only 1 more electron to satisfy its octet? Isn't it? So this oxygen atom requires only 1 electron to satisfy its octet. Done. 1 electron it took from sulfur. Okay. Same way, this oxygen atom is having O minus, 7 electrons in the valence shell. 1 more electron is required. Done. Okay. Now this oxygen atom has 6 electrons in the valence shell. It requires 2 electrons, right? So obviously it will take these 2 electrons from sulfur, right? And lastly, this oxygen atom also is having 6 electrons in the valence shell. It requires 2 more electrons. So it will take up this also. Okay, now going to sulfur, right? Now for sulfur, again, whatever it took, it has to take, right? If it gave 1 electron, it should take 1 electron. If it gave 2 electrons, it has to take 2 electrons. That is how it works, right? Okay, so now you see that 1 electron is gone, 2, okay, 1 electron is given, so this electron will be taken. 2 electrons are given, so these 2 electrons will be taken. Again, this electron, these 2 electrons, everything will be taken. Okay, now it looks like a little complex structure, but it is not. Just look at it carefully, right? Now we'll see how many valence electrons are there on sulfur. Okay, we'll see how many valence electrons are there in sulfur. Okay, now sulfur already had 6 valence electrons. No problem. When the bond was not formed itself, it had 6 valence electrons. Now see how many extra electrons are coming. 1, 2, 3, 4, 5, 6. So totally how many electrons sulfur has? Sulfur has 12 valence electrons. Right? So you can see octet is not the criteria. Octet is not the only criteria. Understood, guys, how sulfur is having 12 valence electrons? Already 6 electrons are there, and 6 more electrons are coming from oxygen for covalent bonding. So that makes it to have 12 valence electrons. Okay, so now how will I represent the structure for H2SO4 along with lone pairs and all that? Okay, now tell me, does sulfur have any lone pair?
No, sir.
No, sir.
Good, right? All the 6 electrons are actually involving in bonding. So there are no lone pairs on sulfur. So sulfur, right? So with these two oxygen atoms, a single bond is formed. So let me put a single bond duo with a negative charge, Okay, and with these two oxygen atoms, it is forming a double bond, right? So double bond O, double bond O, done. Now I have to fill the number of lone pairs for oxygen. So this oxygen atom has 1, 2, 3, 4, 5, 6 electrons which are not involving in bonding. So 1, 1, 2, 3, 4, 5, 6. Same way for this oxygen atom also 1, 2, 3, 4, 5, 6. And for these two oxygen atoms, there are 1, 2, 3, 4 electrons which are not involving in bonding. So basically 2 lone pairs. So 1, 2, 1, 2. So this is how you represent the structure for SO4 2 minus. Now you can ask me, sir, where the hydrogen atoms will come? Can you tell me where the hydrogen atoms will come?
Sir, with oxygen single pair.
Exactly. So basically when I have the O minus, I will add a H plus to this, I will add a H plus to this, done. So you can even, if at all it is proper structure of H2SO4, you would have represented it like this. Done. So that would have been H2SO4. Or if I just remove these two hydrogen atoms, I'm going to have a negative charge on these two oxygen atoms. Understood? Right? So even for complex structures like this, you will be able to draw the Lewis dot structures. Right? So we'll speak more about this, guys. Right? So now you can see that octet or duplet is not the only criteria, even though most of the compounds will, I would say, first period elements generally. When I go for first period, not first period, second period. First period is only hydrogen and helium. Second period, that is my lithium, sodium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, all that, they will generally form only octet. Right? But if I go for period 3, from period 3 onwards, the elements can have more than 8 electrons. Right? So we will try to see what is the reason for this. Right? How is it that it is able to accommodate 12 electrons and all that? We will see some more molecules which are having more than 8 electrons in the valence shell, and some more theories which will explain this particular thing which is happening here in the next class. Right? So any doubts, guys? Any doubt? See, it is very, very obvious that you will get hell a number of doubts, right? But if you are not going to ask, loss is yours, right? Because any doubt in this can be easily clarified. It is okay to have a very stupid doubt also. Please do not think about other people who are here. You can always ask your doubt. Yes, any doubts?
Yes, I have a doubt.
Yeah.
How do you find out what atoms should be in the center, sir? Like here, sulfur. How do you?
Very good question. Very good question. So the thing is, I have to choose the element like this. So you can see that in covalent bond, like basically I need to go for sharing of electron, isn't it? So the thing is, I should choose the element which is going to have the least ionization enthalpy. Okay? I have to choose the element which is going to have the least ionization enthalpy, because the electron can be not exactly removed, but the electron can be easily shared with so many other molecules, so many other atoms. So that kind of atom I take. So generally the rule is that I should take the element which is having the least ionization enthalpy. That's the thing. So out of the sulfur and oxygen, obviously sulfur is having lesser ionization enthalpy. So obviously I put it as a less central atom.
Understood.
Okay, and we'll see more examples. Actually, you can understand, like by the way you more and more practice, you'll not even think like this, which I have to put a central atom. It automatically will come when I do for more problems.
Okay, sir.
Okay. Any other doubts, guys? Okay. So I hope everybody understood. So be ready for more complex things next class, and we're going to make it interesting and easy, right? Okay. Thank you. Bye-bye. We'll see you again.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.